So, hello everyone, and welcome to localhost. My name is Nick, and I'm one of the co-founders of RC. Localhost is a series of monthly technical talks by members of the RC community, open to recursors and the general public. As always, we're excited to see so many new and also familiar faces this evening. If you're not familiar with the Recurse Center, we are a community-driven educational retreat for programmers. We're currently based in Soho, and people come from across the country and around the world to spend 1, 6, or 12 weeks becoming better programmers together in a self-directed and also highly collaborative environment. At RC, you have the opportunity to direct yourself, to pick projects that you find intrinsically motivating, and to spend your time learning the things that you always wished that you could. People come to RC from a really wide range of backgrounds and skill levels and use their time here to work on almost any kind of programming you can imagine, from apps to games to compilers, art, and original research. We are completely free to attend, and we run an integrated recruiting agency to help anyone in our community who's interested in considering new jobs. We also have need-based living expense grants for people from traditionally underrepresented groups in programming. If you enjoyed tonight's talk, please consider applying. There is still time to apply to our batches starting on April 2nd. A quick note about the format of tonight's talk. Julia is going to speak for about 30 minutes, and then after that we'll have a brief 2-minute break. During the break, you're welcome to leave or stretch if you'd like, and then after the break, we'll have dedicated time for Q&A. So please do not ask questions during the talk. There are a few reasons we have a separate time for Q&A. First, taking questions during the talk can be disruptive, and having a break in between the talk and the Q&A allows us to have the talk be time-boxed and also gives people an opportunity to leave if they wish. And we also find that having dedicated time for questions leads to more equal audience participation and better discussions. So without further ado, I'd like to introduce our speaker, Julia Evans. Julia is a programmer and an RC alum from our fall 2013 batch. She lives in Montreal and has been excited about profiling and debugging tools for years and has published several zines on explaining how to use them. Tonight, she's going to talk about building a new Ruby profiler, the first that works on any running process. On a personal note, I'm excited to have Julia back at RC because she embodies so many of the qualities we most cherish. I think most notably, Julia is living proof of just how far you can go when you follow your curiosity and see hard problems not as obstacles, but as opportunities for growth. So please join me in welcoming Julia.
Hello. All right. I'm going to talk about building a Ruby profiler. Some context for this project is I've decided to take 3 months off work to build this because I was so excited about it. This also means that I've been somewhat immersed in the details of the Ruby interpreter. So I'm going to try to make sense, hope that it works. All right. So before I talk about building a Ruby profiler, I think it's important to understand what a profiler is and what it's for. So let's imagine you're on a computer, as one is, and you look at top, and you're like, oh, Ruby is using 100% of my CPU. And you're like, Ruby, what's up? What are you doing? And I think this is a really interesting question, because one really fascinating thing to me is sometimes this would happen at work, right? I work at a company where we use Ruby pretty extensively, and we have a lot of really experienced Ruby programmers. And sometimes I'd be in a situation where we'd be like, OK, we have this Ruby process that's using a lot of CPU right now, and we want to know what it's doing. And no one would know how to figure out what it was doing. And I was like, what's happening? Obviously, the problem isn't with my coworkers, right? Because they're extremely talented and know a lot about Ruby. But I was like, what do you mean we can't know what our Ruby process is doing? It's right there. It's on my computer. I have root. I have a right to know what this program is doing. So I felt like this was some kind of cosmic injustice, right? And so what this talk about is how we can rectify this. OK, so let's start with a demo of the thing I built and how it lets you see what your programs are actually doing. So I have a program running right now. It's called julia.rb. It's meant to represent like my day or something. I don't know. You'll have to bear with me. It's a very silly program. Okay, so it's PID is 21702, right? So what does it mean to ask what is this program doing? So we're going to do something called snapshot it. We're going to get the current stack of this process. Let's make this bigger. Oops. Ooh. Okay. So we have asked the Ruby process what it's doing, and we're basically saying like what's the current stack of the program, right? Like what are the functions that it's running right now? Apparently the Julia process is currently watching Black Panther. Real life. Okay. I'm going to run it again, and it's like sleeping, learning, sleeping, eating, learning, sleeping, learning, cleaning. Oh, cleaning, unusual. Anyway, but I'm trying to explain what a profiler is, right? So what a profiler is it's a program which looks at your program and repeatedly kind of like queries it to see what it's doing, right? So maybe 100 times a second, it's like, what's it doing now? What's it doing now? What's it doing now? And then it can aggregate those in a useful way, like this. So you can be like, okay, cool. Now we are keeping track of the Julia program, and it is spending 70% of its time sleeping, 10% of its time watching Black Panther, and anyway, various other things, right? So this is the tool that I built, and this is the kind of like cool thing that profilers enable. And now that you've seen kind of how it works, I'm going to talk about how to build it, and we're going to talk about the Ruby interpreter a lot. It's going to be great. Okay, so to build a profiler, what we saw is kind of like all you really need to be able to do is collect one stack trace from a Ruby program, right? Because if you can collect like one stack trace to figure out what it's doing right now, you can also collect like 10 million stack traces to figure out like what it's doing over the course of an hour, right? And you can just like ask what it's doing every 10 milliseconds. So collecting one stack trace does not seem like it should be that hard, but it's really hard, which is why like there was no tool to do it. But you might think like, okay, but this is easy, right? Like if you're inside the Ruby program, then getting a stack trace is pretty easy, right? You can like run like thread.current.backtrace. There's lots of different ways to get a stack trace if you are like, if you can run code inside your Ruby program. But the issue is that like, so there are a lot of profilers that did this, right? I did not write the first Ruby profiler ever. That's silly. There is a great existing profiler called stackprof, which runs inside your Ruby process and figures out what it's doing. And the issue with this was that if you wanted to profile a new program that you'd never profiled before, then you have to edit the source code, right? So you need to like get the gem to profile it, like require it in your program, edit your code to start profiling it, restart your process, get the data, and it was like a lot, right? And of course this isn't impossible. Like it's something that probably anybody could do given some time. But in practice what I found is that people wouldn't profile their programs because they felt like it was too much work. And I was like, this is no good. I love profilers. I want everyone to be using profilers, right? I want to do something about this. So even though I love stackprof, I felt like it wasn't really working for me. And I wanted to build something better. So the goal is to build a tool that can profile any running Ruby program, right? You know, you're just like, this is a program. What are you doing? And then you can just find out right away. OK, great. So how do we do this? First important thing to know is that the Ruby interpreter is a C program. So you have the Ruby interpreter, and then it'll run your Ruby programs, right? Which is like whatever.rb. So that's cool. So the way most profilers work, the way all other Ruby profilers work, basically, is you have your Ruby process, you have the interpreter, you have some program, and you have some like profiler code that runs inside this process, right? So everything's in the same process, profiling happens, everything is great. This is not what we're doing. Instead, we have the Ruby process over there in a separate process, and our profiler is kind of like coming in from outside, and it's like, what are you doing? I will spy on you. And what this gives us is kind of like the flexibility to profile anything that's happening, right, without being able to like change, like even if we don't have access to the the internals of the Ruby process. OK. So how do we do this, right? This sounds really cool, but like how is this possible? The program is called rbspy. It's a Rust program. This is going to become relevant later, but it's not relevant right now. And we're going to use a really important superpower, which you may not be aware that you had, which is on Linux, you can read any process's memory. So if you have a program and it has memory, you can just read any part of it that you want. So there's a system called process VM readb, and you give it a PID, an address, and the other process's address space, and a length of memory you want to read, and then you can just get it. Which you're kind of like, is that allowed? Well, you have to root, right? Like, otherwise it would be like a really extreme security vulnerability. Like, but you can do this, right? It's fine. So that's cool. So like if you have the Ruby interpreter and you can read like any memory that you want out of it, then surely you should be able to figure out what it's doing, right? Why not? There's no problem. Okay, so let's talk a little bit about how the Ruby interpreter works. We're not going to talk that much about it, but we need to know some things. Okay, so at any given time, in your Ruby interpreter, you have a like object that represents the current thread, which is somewhere in memory, and this has like a pointer to a stack. So this is the Ruby stack. So like this is a bunch of whatever structs that are all together, and each one of them represents like a part of the stack in your Ruby program. So let's say at the top you're running like myprogram.rb, it's on line 30, and it's running the function like do thing, right? So if you have our current thread, it points to like the top and the bottom of the stack, so you can so that the Ruby interpreter knows what code it's running, and then you can see what it's doing. And what we need to do in our profiler to figure out like that Julia is currently watching Black Panther or whatever, is we start out at like the address of the current thread, and we're going to need to follow a bunch of pointers inside the program. So you start out like here at the current thread, and then you find like the top of the stack, which is this like struct called like rb control frame t. None of this is that legible because that's like how it's like Ruby interpreter internals, which like no one expects you to understand when you're writing Ruby, but which you have to understand when you're trying to like spy on it. So basically, you read some memory, and then you find the pointer to the top of the stack, and then you read some more memory, and you're like, oh, ISEC. ISEC means like the thing with the function and the line number and stuff. And then you're like, okay, that's somewhere else, and then you go read the memory there, and then you find like the right offset for like another part, and then you go read some more memory, and you read some more memory, and once you've gone like 6 steps, eventually you find the string Black Panther, and you're like, okay, got it. I now know what Julia's doing. Okay, so that's like the big picture of what we're trying to do, and I want to explain like what you actually have to do in real life to get it to work, because this was like extremely not obvious to me when I started. Okay, right, so we now maybe hopefully believe that reading memory out of another process is easy, but like figuring out which memory exactly to read is hard, because your Ruby process might have like 2 gigabytes of memory. You're like, where in there is like the right thing, right? It's kind of like finding a needle in a haystack. Okay, so the first thing we need to do, hard thing number 1, there are going to be 2 hard things, and I'm only going to explain one of them. It's not this one. But in the questions, you can ask me about this later. So the first thing you have to do is find the address of the current thread. So this one is a global variable in the Ruby interpreter. It's called Ruby current thread. It's pretty helpfully named. And the way you find it is you look it up in the symbol table. I'm not going to explain it more, but you can get me to explain it in the questions. But let's for now assume that we can do this. One fun way, if you are excited about like inspecting the internals of C programs, as apparently I am, is to use GDB. So in GDB, I can say like, hey GDB, GDB is a C debugger, which makes sense because Ruby is a C program, right? You can say like, okay GDB, what's the address of like Ruby current thread? And it'll tell you. It's like, oh, it's 0x82d5d0, Julia, obviously. So that's where we're going to start. And I can tell you more about how to like reproduce what GDB is doing and how I do that later if you want. Okay, so we now know the address of the current thread somehow. And so we can go read the memory there, right, using our like reading memory superpowers. And then we find this. We're like, okay, cool story. Right? So like this is what our program is seeing, right? You're like, well, what am I supposed to do with this exactly? Right? Like, because like in our picture, there was this pretty diagram, and it was like, okay, cool. There's this field. It's called CST. It points somewhere. But when you look at it, you're like, oh, right, okay. This is not how C works. C is just like there's a bunch of binary. Okay. So what's going on, and how can we resolve this? So if we go look at the Ruby source code, there's this struct called rbthreadstruct, which represents a Ruby thread. And so this struct is basically like the stuff that's here. Like every field in this struct is represented by like some of these bytes up here. So for example, like this thing vmlt node is like it's at the beginning, so it's like this stuff. Oops, it's like this stuff here. Okay, so then that means that this thing CFP, which is like the control frame, which is the first thing on the stack, which is where we need to go, is like one of those things. Yeah, and it turns out that it's which is 0x like 7F09, whatever, blah blah blah. And it's at the offset like 48 bytes, right? But how can you know that, right? How can you know that it's like those bytes and not like some other bytes? So there are two ways to find it out. Way one is dwarf. What like a Disney character tells me. No. So basically, dwarf is extra debugging information that's generated by the Ruby compiler, not by the Ruby compiler, by the compiler. Like when you compile Ruby, the compiler can like store extra information, which is like, okay, like this struct, like for every member of this struct, like here's like the offset of it. Yeah, like here's how far it is offset inside the struct. So it'll be like, oh, this one's at 48 bytes, this one's maybe at 40 bytes, this one's maybe at 56 bytes, whatever. So that's great. This is if you use like GDB as a C debugger, and you kind of like and if you use it to like navigate a C program, it uses dwarf, and it'll like complain at you if you don't have the right debugging information. So dwarf works. I wrote a prototype of this program using dwarf in 2016 at RC Never Graduate Week. So this was like May 2016, and I was so excited because it worked, which was like huge. But there's kind of an issue, which was like, well, like people don't always actually have debug info, right? Sometimes they haven't compiled the Ruby with debug info. In particular, if you install Ruby like on Debian with like apt-get install Ruby, by default you don't have debugging info. And then so like, are you just gonna tell people like, sorry, doesn't work for you because you don't have debugging info? Like that would be like reasonable, and that's what like many people do, right? Like I think no one would get mad. But I was kind of mad. And I was like, well, what? Like, I want it to work for everyone, right? Like, could I just make it work for everyone? Would that be allowed? So I was thinking about this in December when I started working on this project again. And I was like, well, look, what if we didn't use dwarf, right? And I saw this other profiler which didn't use dwarf. And I was like, oh, cool. Maybe we can do this. Maybe we can make it happen. And spoiler alert, I made it happen. So let's talk about how I did it. Okay, so let's talk about C structs. So we have this struct. Let's say that this is because we have the Ruby source code, right? And we have the Ruby source code for every past Ruby version. I can just go to my clone of the Ruby source code on my computer and do like git checkout v2.2.6, and I'll have the Ruby source for Ruby 2.2.6. So if we have this struct, the cool thing is that like C structs are basically laid out in the same way in memory, always. Given that you have the same code, so you can kind of like just know. Like as long as you have the source code, which you do, right? And so I have all the source code on my computer, and I know that like C structs will kind of be represented in the same way in memory, no matter what. And so like surely I can just like maybe build like some kind of magical table, which is like, okay, so in Ruby version 2.0.0, it's like this, and then at 2.1.0, it's like this. And then like, no, right? And I could just store all these and like memorize them and put that into my program and have it like figure it out. Yeah. So this like doesn't really seem practical, right? Like it seems like a lot of work, and like it might not work. But there are very exciting things that are going to happen. Okay, so this is where it becomes relevant that my program is written in Rust. There's this extremely cool program called bindgen. And bindgen is what it does is it generates Rust versions of C data structures. So what I can do is I can write a bash script, because bash scripts are like the root of everything that is good in the world, right? I can write a bash script which takes every Ruby version, right? And I can be like 4x in the list of all the Ruby versions, and then I can be like cd checkout of my Ruby of the Ruby source code, and then I can do git checkout v whatever, and then I can generate Rust versions of all the data structures in that in the Ruby source code for that Ruby version, and then I can put it in a file called like 230.rs, like for 2.3.0, and then I can repeat that for every Ruby version, and I can end up with these like large, incomprehensible Rust files full of structs for every Ruby version, which is fine because nobody has to read them. I can just check them into my Git repository, and we won't think about it too much, right? So this is fine. This is great, and what this means is because if I define a Rust struct the right way, like if I say like, okay, here's a struct in Rust, but like pretend like it's a C struct, right? Like pretend that it's represented the same way, then I can use these, like I can kind of like teach the Rust compiler about the representation in memory of all of these C structs that I care about, which is very exciting. Okay, so now I can tell you how we copy memory from the Ruby process in a way that works and like lets us get the right fields and figure out how the memory is laid out. Which is amazing, and this is like effectively real code, and it's like 4 lines of code, which is like extremely exciting. Okay, so here's how it goes. We can say like, okay, let's say we want the rbthread t or the rbthread struct struct from Ruby 2.3.0, right? So I made this like huge file called Ruby 2.3.0.rs. With like all of these definitions, which is very long and which I've never looked at, but it's fine. And then I can say, okay, now because we know how to copy memory, right? So I'm like, okay, copy memory out of my target process at this address, and I know that I have the right address, and like read like the size of this struct, right? Whatever it is, like maybe it's 200 bytes or something, right? Maybe read probably more, maybe 700 bytes. So maybe you read like 700 bytes of memory. Or so. Okay, so now I've copied my memory, and I have it, right? I have like, basically you can just imagine like some array of bytes. Like I have some kind of like incomprehensible thing. And you're like, okay, what now? What now, Julia? But then I can say like, okay, this is a type that you know about Rust. This is just like this like rbthread t type. So in Rust, I write more unsafe code than most people maybe, because I'm just like, just pretend like that memory is this other thing. I promise it's fine. So like Rust is not like predisposed to believe that it's fine, but you're just like, look, fine, which is what unsafe means. Unsafe means it's fine. I promise. In this context, it's kind of like, I feel like maybe it should be called I promise. Like maybe it's not the right keyword. I think unsafe in Rust means like I promise it's fine. Okay, and then this just means like just pretend this thing is this other thing, and then I can just say like I want this field called CFP, and then I can just say thread.cfp, and I have the field of my struct that I want, and then that's the address of the next thing I need to go to, and then I can keep going. So this, well, shockingly, this like actually works, even though we're just like copying memory out of another process, and then just like reinterpreting it as a type that we have that we decided was right, and like. It all actually seems to work, and that means that I can write a function which is like, hey, here's how you like get the stack. This is not the real function is like bigger, but this is sort of what the code for the function looks like. So you're just like, okay, to get the stack, like you find like the right start address, and then you copy a thread, and then you're like, okay, then take like the .cfp attribute of that, and then copy some more memory. And then like take like the .isec value and then copy some more memory. And then you just keep on copying memory, and then eventually you find a string buried somewhere like down the chain of things that you looked for. And it says like Black Panther, and you're like, Black Panther, that's what she's doing. She's watching Black Panther. So you might have a question, which is like, do we need to recompile this profiler for every Ruby version, right? Because all of this was specific to like Ruby 2.3.0, right? Like this is all like compiled to work with like a very specific Ruby version. So you might say like, okay, well, having to recompile your profiler for every different Ruby version doesn't sound like fun, Julia. You said you were going to make this easy. This doesn't sound easy. But what we can do is we can just write like 40 different versions of the same function for every like different Ruby version, right? We can just be like, well, here's version 2.2.0 and here's version 2.3.0, and you can basically just like copy and paste the same code, right? Except copying and pasting is boring and like bad programming practice. So the answer when you want to copy and paste code is you use macros, which are like copying and pasting code, but like it's allowed and good, right? So I Googled like how to use Rust macros, and then like 20 minutes later, I just like defined 20 different versions of my function, and it all totally worked. And I was like, what happened? Like, I feel like mad with power. And that was extremely exciting. This is the only piece of real code from my profiler in this talk. This is where I decide like which get stack trace function to use. So it's not like really like smart or clever. I'm just like check the version, and then if it's 2.2.1, run the 221 get stack trace function, right? And I just have like 40 of these. And then I just decide which one to use based on what I discover the Ruby version is at runtime of the program targeting. And it all kind of works, which is weird. Okay, so I have some like, this is most of what I have to say. I don't know how much time I have left, but I think we're good. Some thoughts about this. I think that building programs that seem a little bit impossible is kind of fun. Like there are a lot of things in here which are sort of a bad idea, but the program actually works for people, which is surprising and weird. Like people will be like, oh yeah, I just used it to figure out what was going on with my program and it worked. And I'm like, do you know what black magic is happening in this program? And they're like, yeah, it just works, it's cool. And you're like, wow, that's incredible. And I think like building a prototype was really important for me. Because like taking 3 months off work to work on this weird thing that I was excited about was kind of scary. But the fact that I already had a prototype that like kind of worked made me feel like, well, I could probably do it because I have this like kind of sketchy version that worked already. So maybe I can make a version which is not sketchy. Like why not? It'll be fine. Even though I changed a lot about how the old sketchy, like I made a lot of changes to how it worked. But like having a prototype really helps build confidence. I don't really think I could have done this if I wasn't doing it in Rust, because Rust is like, I don't know, why couldn't I have done this without doing it without Rust? Rust is really a lot easier to use, I find, than like C. Like I don't know C, I also don't know C++, and I feel really confused about them. And with Rust, I feel like I can write programs, like systems programs, and I can get stuff done, and I can like implement my weird ideas, and it makes me really happy. And my partner, Kamal, also helped me a lot with Rust, and reviewed a lot of code for me, and came up with an amazing testing strategy. Maybe we can talk about the amazing testing strategy at some point. Because like, how do you unit test this? We could talk about it. He came up with that. It was really smart. And I think like my favorite thing about this though is that like I really enjoyed like doing all of these like really hard, weird systems things with the goal of making it easy to use, right? Because like the reason we like did this weird stuff where we like read the memory and then use bindgen to generate like the bindings for like 40 different Ruby versions, and then use macros to like generate all these different versions of the C function, was that like I wanted it to just work for people, right? No matter what Ruby version they were using, and like no matter and like whether or not they had debug symbols installed on their computer, because installing debug symbols is annoying if you don't have them. And I wanted to make like Ruby profiling more accessible, and I feel like it's really cool to do like hard, weird things to make things simple and easy for people. That's all. Am I working? Good? Okay. Yeah, let's start with Andy.
Do you pause the target sort of process while you
Great question. So the question was, do you pause the target process while you read its memory? I was hoping someone would ask that, so I'm happy it was the first question. Okay. Because many profilers will pause the target process. This is like good and bad, right? The good thing about pausing the target process is that you know that the process is in like a somewhat consistent state, and that it won't go start running another function while you're in the middle of reading its memory. And the bad thing about pausing the target process is that you have to spend time to slow it down, right? And it's a little scary to do maybe if it's production and you like don't want to impact the process's performance. I don't pause it. I just let it keep going, and I'm like, we're in a race, and I'm probably going to win. Because I'm in Rust, and I'm fast, and that's it. Yeah, so I don't pause it. It seems to work fine, which is kind of wonderful to me, and I think it's, I mean, like sometimes there are errors, but if there are errors, I just kind of log them and move on. Because it's a statistical profiler anyway, so if there's a problem, it doesn't really make that much of a difference. And it makes me feel a lot better about running it in production. Yeah. Yeah. How do you test it? Cool. This is perfect. Okay. So how do you test it? So my partner Kamal came up with this really cool testing strategy because it's like you're trying to test that like when you read the memory of like some kind of arbitrary process that it'll work out correctly and it'll give you the right results. So the idea he came up with was like, well, take core dumps of a bunch of Ruby processes, right? So core dump is just like a snapshot of the process memory. Like you just like literally save its memory to disk. So take these core dumps and then like run your code on like that core dump on disk as if it was the process's memory, and then see what happens. So I just took a bunch of core dumps and then like checked them into a Git repository and then run them and then turn it into unit tests, and then I know that it works. And it's amazing. It makes me feel a lot more confident. Yeah. You. I haven't thought about having threads yet. This is like a to-do. To-do. Think about multiple threads. Yeah. Yeah. You.
How do you find the address to start reading?
Right. I promised I would add to that. Okay. So the question was, how do you find the address to start reading? Okay. So programs sometimes have what's called a symbol table. And the symbol table is like it's basically like a lookup table which has like strings and addresses. So it's like it'll have a string which will be like Ruby current thread, and then the address of that thing inside the inside the binary. So which is interesting, right? Because like usually when you think of like things inside a binary, you think of functions, right? You're like, oh, like this function has like some address, but there are also variables inside the binary. And so you can use the symbol table to find its address. But the address inside the binary is like not, like it's just like some offset. Like it might be like, let's say the Ruby current thread thing is at like, whatever, it's like 2 kilobytes into the binary, into like the Ruby binary. This is like not actually where it is in the process's address space. So what you need to do is look at something called like the process's memory maps. So like every program has a bunch of what are called memory maps, which are like different areas of the process's memory. And so the binary, like the process's like own binary, is mapped inside its own memory, which I guess is not obvious, but it is. And then so what I needed to do was like figure out like where the binary is mapped, and then take like whatever that number is, and then add it to whatever the Ruby current thread address is. And then once I added those two things up, I got the result, and it worked. There's maybe an additional complication, which is you can also, for example, when you apt-get install Ruby on Debian, it will strip the symbols, so there are no symbols. So then you're like, uh-oh, can I still do it? But I decided to do it anyway, because it's like more fun, right? So I was like, okay, well, if we don't find the Ruby current thread symbol inside the binary, what we do is we just like, we're like, well, we know it's in there somewhere. So you just kind of start looking and try each one of them and see if it works. And then if it does work, you're like, hey, sweet, I found it. And like basically what I do is I just like try to run my like get trace function, assuming that that's the right address. And then if it works, then I'm like, great. And if it doesn't work, then it doesn't work. And I just keep going. And surprisingly, this like actually works. And you kind of can just like use this like weird heuristic to find the right address, even if there are no symbols in the theme of do impossible things. Who is next? You. You. Yeah. You. So the question is like, are there these exploit mitigation things where when a program loads things into its memory, it'll it's called like ASLR, address space layout randomization. I think that's what you're talking about. And it'll like load its binary into a random place. I don't understand a lot about security, so I don't. But what I've observed is that I can tell where that thing is being loaded, and then I can just find the right offset, and then I know where it is. So it doesn't seem to be a problem, but I don't really understand this super well. It's something I've been wondering about, but I don't totally understand it. You at the back.
So you have all these functions for different versions of Ruby. How do you determine which of these is the one that you use?
So the question is, you have all these different functions for different versions of Ruby. How do you know which of these you should use? So there's also a Ruby version symbol, which like so somewhere basically inside the Ruby binary, there's like a string which says what version it is. And so you can look up the Ruby version symbol and figure out what version it is just by reading that string. And that string is there even if the symbols are stripped. So it's OK. So yeah, it's just a string in the binary. You can just find it. The other thing that I thought about doing, because I was scared about this, and I was like, well, if worst comes to worst, I can just like take the executable and then run it with -- version, and then parse the output of that. But I didn't have to resort to that. But I did think about it. You have a question.
Yeah, so you mentioned using a macro to generate all the different versions of the and then you showed that those exist within the program. Was that the macro expanded those, like the output of the macro, or was the macro doing something else?
The macro is doing something else. This is just actual code. These functions are all functions which were like generated by a macro, but I just typed out all this code. Yeah. You at the back. So the question was, could you elaborate on the weird heuristics used to figure out like what the right thing is? Okay. So the weird heuristics. So like every binary has a section called the BSS, which I don't know what it stands for. But basically it's where so C binaries will have like global variables in them, and global variables are kind of like they're not. So like okay, so in a C program, you have the stack and you have the heap. And that's like most variables are either on the stack or in the heap. But some variables, like global variables, are not in those places. They're kind of like inside the program's binary. Like there's like a part of the program which is like blank, which gets like mapped as like read write, and where you can write things, and that's where things like global variables live. But this is this is something that you can find if you look at a program, you can figure out like where it's mapped. And so I basically like looked at like the section of memory, and I just iterated through it like 64 bits at a time, because I knew the thing what I was looking for was an address. So I just iterated through it like 64 bits at a time, and then pretended every 64-bit thing I saw could be an address, and then tried it out. And then like basically by pretending that it was the right answer, and then like trying to use it to get a stack trace. And then if that worked, then I said like I win. Yeah. Other one, Bert.
Other ways in which, like, if you run this on your Ruby program production, are there things you can do like aware of or watch out for, or is it like, hey, you're the profiler?
So the question is like, can you run this on your Ruby profiler in production? Like, is there anything else you should watch out for? There's nothing I'm aware of that you should watch out for. I always feel worried making statements like this because I'm like, well, like, what if there's something I don't know about? And like, systems programming is weird, right? But I'm not aware of anything. Like, what can go wrong? Like, this program sometimes uses a non-trivial amount of CPU itself. So like, and I want to work on its performance a little bit so that it uses less CPU. It writes some amount of data to disk. But other than that, I'm not aware of anything. Yeah. So the question is, when you decided to take a sabbatical, did you know you were going to do programming? So the way I decided to do the sabbatical actually was there's this program called the Segment Open Source Fellowship, and I saw this tweet about it, which was like, hey, do you want to do an open source project? Well, we're going to like pay you to do this for 3 months, which is actually what I'm doing. And so I saw this tweet about it. I was like, oh, cool idea. So I clicked on it. I typed some stuff into the forum. I was like, what would I do? And I was like, Ruby profiler, yeah. Because I'd done this prototype before, and I was excited about it, right? So I was like, I'll do that. And then I like clicked submit, and then I forgot about it, right? And then they got back to me a few weeks later, and they were like, we accepted you. And I was like, oh. Like, I wasn't expecting that. And then I figured out with my manager how to take time off work to do it. But yeah, I guess I talked myself into it by applying to things on the internet without thinking through them. Jesse. So the question is, presumably you're going to get random weird pointers to nowhere if you are in this race with the Ruby interpreter and things are going to go wrong. How do you make sure that your program doesn't segfault, basically? So the kind of cool thing here is actually because we're reading memory from another process, we need to make a system call every time we want to read its memory. And so if it fails, then what's going to happen is that the system call will just like kind of return a failure. And then I can just like take that failure and then like bubble it back and just be like, oh, something went wrong. Oh well, let's try again. So it's kind of cool because you're not dereferencing at the address directly, and because you have to do it through a system call, it's like a little bit harder to segfault, right? Yeah. Yeah. So the question is, with bindgen, does Rust guarantee that if you have a Rust struct that looks like a C struct, they'll have the same in-memory layout? So what you kind of have to do, maybe I could just open a text editor really quickly and type like a few characters. Basically, what you do is you put this on top of your Rust struct, and then you're like struct blah, and then the Rust compiler will represent it like it's a C struct. So you just put this little thing on top. So like normally Rust structs are not necessarily represented like C structs, but you can tell the compiler to do it that way, and then it will. So all of the code which bindgen generates says this. And you can do the same thing with functions in Rust too. Like you can say like this is a C function. Like represent this as if it were a C function, and you're like extern C and blah, something like that. So bindgen generates like structs that look like this and functions that look like this. I probably got the function thing wrong, but it's something like that. Mark.
Measuring how much time programming spending each section as the purpose of the output. Like if you're calling it size, if you're trying to see it at a time, or you're trying to write it for a really long time,
the question is like, how do you measure how, like when you collect the information, like how do you measure? So I'm using it mostly for long-running measurement. Yeah, and this is actually a really interesting question. Well, we can do another demo maybe, and maybe that's a good idea. So let's run another random Ruby program, which is rubocop. So rubocop is this linter. The reason I like it is that it takes a long time to run. So it's like a good thing to run a profiler on, because like I have lots of time to start profiling it. Okay, so we can run it on rubocop. Okay. Okay, cool. So like here I'm recording what rubocop is doing over like a period of time, right? Like this is a like summary output of everything that's happened since I've been recording it. I'm recording it 100 times a second. And so you can see it spent like 6% of its time just in the advanced function, whatever that is. Who knows? And then so I like print out this this output while I'm recording. But the other thing I do, stop. Okay, is generate like a visualization when it finishes. Firefox. And then it's like, oh, this is like the picture of what your program was doing. Yeah, I guess I should have showed that in the demo. I forgot. So this is a flame graph, and it was actually really important to me to like build visualizations into the program, because so often like profilers will give you like raw data and they're like, okay, it's up to you now to figure out what to do with this, and then you're like, like how do I use a profiler again? What's happening? So I generate this, and then there's also an option to generate call grind data, which is another popular format. Mark. Yeah, it'll do it. It's kind of hard because like, do I use it for that? I would use it for that. Yeah. Sorry. The question of do I use it for that is a little weird because I don't have any Ruby programs to profile right now because I'm not working. Does that make sense? So it's kind of like a weird. But yeah, no, I do use it for that. Sorry. Yeah, Austin.
Do you have any stories about difficult debugging problems or interesting debugging problems that this has solved or could solve?
Do I have stories about problems that this has solved or could solve? This is a good question. I would like to have more, and people have been using it to like make their programs faster, which has been very exciting to me. Someone was working on this program called Cocoapods, which is like this program for Mac that helps you with your dependencies for iOS stuff. I'm like not really familiar with this ecosystem, but someone used it to make Jekyll faster. I don't think I have any I have a lot of like weird debugging stories about building it, but I don't think I'm aware of like any particularly thorny problems solved yet, because people don't give me enough stories. If you tell me stories, I'll be very grateful. Yes.
What are some of your weird debugging stories about building it?
What are some of my weird debugging stories about building it? Okay, so one thing that happened is I wrote about this on my blog. I was building a Mac port because I was like, oh, it'd be really nice if this worked on Mac, right? And I'd never built a program for Mac before. But I was like, this will be fun. I can do this. Rust works on Mac, right? But, the compiler targets Mac, so it should be fine. So I started doing it, and I built this prototype, and it seemed to kind of work. And I was like, oh, cool, it kind of worked. I spent maybe four or 5 days on it, and I got it to work. I figured out how to read memory out of another process on Mac. And I was like, cool, this works. And then someone sent me an email, and they were like, so I ran your program, and it froze my computer. And I was like, oh. And then someone else was like, oh yeah, I also, I just ran the tests, and the tests froze my computer. So it turns out, anyway, so I managed to reproduce this finally, and I got it to freeze my VM, or not really freeze my VM. Well, so it was interesting, because like the meaning of like froze my computer was kind of weird, because what they said specifically was like weird stuff started happening, and then I opened Activity Monitor, which is like the thing that tells you what processes are running, and then nothing was there. And I was like, what do you mean nothing was there? What's happening? I managed to like reproduce this, and then I ran like PS to see what programs were running, and when I ran PS, it just hung, and like nothing happened, and I was like, but there are still processes. Like I see them running, right? Like the processes didn't disappear. So it turned out that what happened is I was using this like sort of system call called task for PID, which takes a PID and turns it into like a mock task, which is a Mac thing. And it turns out that if you exec a program on Mac and immediately after that run task for PID on that PID, then it can freeze your computer on High Sierra. And this is why also there's an issue on the program htop, which will like investigates like what's going on with programs, where htop can freeze your computer. But if you stop htop, your computer will come back if you can do it. But it's like yeah, it's a real issue. It's new in High Sierra, so I guess presumably Apple will fix it at some point. But I was like, cool. I programmed on Mac for like 4 days, and then I found a kernel bug. Like that's like that's weird. That like wasn't the result that I expected. But I don't know, that was what happened. That was weird. Yeah.
Yeah, I was wondering if there are any other profilers that you like really respected or looked up to when thinking about this. And sort of on the flip side, is there anything nearly as cool as this on other languages that you're aware of, like Python or anything really?
Yeah, cool news about Python. I was actually really inspired, I should have said this before, by this profiler for Python called Pipelame, which does a very similar thing. It works in almost exactly the same way, except that it pauses the process instead of not pausing it, because I guess they decided to like not just be like, I'm fine, I'm gonna win, like, and instead like maybe take a more measured approach. But yeah, it's called Pipelame. It seems to work great, and it's actually a lot more. It doesn't do as weird things, but like, which is good. It's like more, yeah. I would definitely look up Pipelame. And also like other programming languages have good profilers. Like for example, the whole Java ecosystem has great profilers. And I've been really inspired by that. Because like, well, so for example, like YourKit is this proprietary profiler for the JVM, and it's just like outstanding. Like it's like so much better than like anything Ruby or Python has, like by like such a huge margin. And I wish that we could have tools that are that good. And this, like, it's like part of what made me want to make something like this, because it's like a tiny step towards that. Yes. So are there things that you would recommend to Ruby maintainers to like make this kind of tool easier to write? I've been thinking about this. And I was kind of, because like, well, there's an issue where like I'm only using like internal structs inside the Ruby VM, which are like kind of intentionally unstable. And so like asking that they stabilize those is like not reasonable, right? Obviously. But Ruby is getting a JIT, right? Which I was just reading about, and I was like, oh, well, other languages that have a JIT, like, make sure that their JIT makes it easy to work with profiling tools. Like Java has a JIT and it works really well with profiling tools. Node has a JIT and that works well with profiling tools. So I was like, well, Ruby's JIT should work well with profiling tools. And so I was thinking of looking into that and like seeing if there's anything I can do there. I don't know. I haven't thought about it that much yet, and I haven't looked into how the JIT works. Yeah. Oh, great question. Now that you have this magical power to poke at the Ruby internals, what do you want to poke at? So one thing that I was thinking of doing, well, another thing that I find very frustrating about Ruby, and I think about most programming languages, is that it's very difficult. Like if your program is using a lot of memory, it's very difficult to know why. And I don't really know what to do about this yet. Like I don't have a clear idea of what to build. I made this demo, which does this cool thing where every time you allocate memory in a Ruby program, it kind of instruments the Ruby interpreter, and every time it allocates memory, it records the current stack, and then it reports the stack, and then you can say okay, these are the functions that are allocating memory the most, and you can kind of live track memory allocations. So I have this demo that does this, and it's kind of cool. I was thinking of making it into a real thing, but I'm not sure. Another thing that I was thinking of doing with memory is just if you have a core dump of a Ruby process, can you figure out what objects are in it, right? If you have a 2 GB core dump, can you figure out what is in there? But I think maybe the issue with that is that what you're likely to find, I would guess, is that there are a lot of strings. But if you don't know where the strings come from, it's maybe not that helpful. So, and that's what people have told me, is just being able to know what kinds of objects they are generally won't help you, and you have to actually know where those objects were allocated to be able to make useful conclusions. So I don't know. That's what I've been thinking about, but I'm not sure yet. Danielle. So what kind of output do you get when the Ruby program is running a block that doesn't have a name? That's a great question. You can actually kind of see it here. Okay, right here. So you can see it says block in iterate until no changes. And actually I didn't do anything special to make that happen. Inside the Ruby interpreter, it reports the label of this. It kind of has the stack, and then it reports the label as just the string block in iterate until no changes. And sometimes it'll say level 2 or level 3. But yeah, that's what happens. Are there more questions? Oh, you have another question. So the question is, there's you notice that it said C function unknown line 0, just not very descriptive. And can you know what C function it is? I don't know yet. I've been trying to decide if I'm going to solve this, I guess. I haven't looked into it a lot yet. It seems like it should be possible. But yeah, I don't know. I might do it. I'm not sure how important it is, kind of, but maybe it's important. I don't know. I can't tell if it's important or not. But it seems fun. Yeah. Are there more? Oh, sorry. Yeah. So the question is can we talk more about the macros? Would it help if I showed you the code? Let's look at the code. Oh no, I need internet. Okay, we can do internet. Oh no, that won't work. How do I get internet? Is there internet? Yes. Oh no, but I have code on my computer. I feel very silly. I have VI. I have this weird habit of go to GitHub to look at my own code, even though it's on my computer. I don't know. I don't know if anyone else does that, but I do that for some reason. Okay. So what is a macro? Where could we do a macro? Okay, so my Ruby macros, I made them look simple, but they're actually kind of weird. Okay. So here's what my macros look like. I have this. I'm trying to define this. Where is it? This function called get stack trace. This thing gets stack trace. And so what I do is I'm like, OK, while we're defining all these functions, what you need to do is it takes like one parameter, which is a Ruby version. So I'm like, OK, define a new like Rust module named after this Ruby version. And then in that, like import from the Ruby structs, like from the bindings, the right ones for this Ruby version. And then define all these other functions, basically, which are also macros. It's a little bit of a mess. So for example, there's this get Ruby string macro. Macro get Ruby string. Sorry, there's like a lot of macros. Where are you? OK, here you are. OK, so then like this macro is basically just a Rust function. Like it doesn't have any parameters, so it's always the same for every Ruby version. And so like this one is literally just like copying and pasting the code. So like to get a Ruby, like so what this does is it takes like the address of like a Ruby string object, and then it returns like an actual string. And then it like copies some memory and does some. So Ruby strings, we can learn about how strings are represented in Ruby. Is that interesting? So the way strings are represented in Ruby is you have like this struct, which is, I don't know, some amount of bytes, and if the string is short, then like the string is represented like inline in the struct. So if it's like, let's say like 20 characters or something, then you'll just have like, then the string will just be like part of the struct. And then if the string is long, instead of having the string, like if it doesn't fit basically, then you'll have like a pointer to the string, which will be allocated on the heap somewhere. So I kind of need to check to see like what kind of string it is, like if it's right there or if it's somewhere on the heap and I need to go find it. And then if I need to go find it, then I need to like go copy some more memory, which is happening here. And then you can see it at like a lot of different points. I'm like, if there's an error, then return an error. Otherwise, it's OK. So there's a lot of places where and also like if I try to read something as an invalid string, then I'm like, oh, this wasn't a valid string. Give up. Like, so did I answer your question at all? Yeah. So the first one, I guess, takes a parameter. Like this one depends on the Ruby version. So it like, then the only thing it uses the Ruby version for is to like import the right types for that Ruby version, which is this use statement here. Does that make sense at all? It's like not extremely good code. Like it's kind of a mess. These aren't like very good teaching macros. But this file is like, so this file is like everything that makes it possible to read memory from Ruby processes and like interpret it the right way. And it's like 700 lines, which isn't like that much, because it works for like 40 different Ruby versions, which I thought was cool. One more question. Who is it? It's you.
I feel like, yay, radical! Like I did the thing that I wanted to do, and I'm super happy with how I spent my time. And I'm like, ooh, I wish I'd also added for.
I feel really happy. Oh, so the question is like, do you feel like, yay, I like did everything, or like, oh, I wish I'd done something differently? Did I use the time I wanted to? I think so. Yeah, I feel like I used the time the way I wanted to. I spent a lot of time programming, which is what I wanted to do. I still have a month where I can like investigate various things, most of which you've already asked me about. You asked extremely good questions about like everything I've been thinking about. I feel good. I feel really happy that I took a sabbatical to work on this thing. And I also feel like I'm happy that I'm not going to be working on it forever, because it is like like sitting at home coding by myself is like maybe something I only want to do for like a limited time. Like, and I'm excited to go back to working with my coworkers and stuff. Like, yeah.
One more big thank you both to Julia and to eBay for hosting us this evening. So thank you all. Our next localhost talk will be on March 20th. The speaker will actually be Andy Kelly, who's sitting right here. And he will be talking about Zig, the systems programming language he's writing, and how to write software without bugs. So we hope that you will join us for that. Yeah, I think it's going to be a great talk. So RSVPs for that will open up next week. So thank you so much for spending your evening with us, and happy programming.